Hello there, my name is David Martin and I'm a director for Primekks based in the UK. I'm really pleased to be able to join you on this webinar, and I have to be honest, I could talk to you all day about concrete. However, I've been advised that I have only a few moments, 7 or 8 minutes, to talk to you about my journey to Primekks, what Primekks means to me, the benefits of the Primekks system as I see them, and to provide you with an example of works executed here in the UK before taking any questions. And I really do hope you have some questions, because I can talk for a long, long time. My journey to Primekks then. How did it all begin for me? The answer to this is relatively simple. I studied civil engineering, graduating in 1985, and I was commissioned into the Royal Engineers. So I have both a military and a civilian engineering background. And as an engineer, I spent my formative career years working predominantly with plain or plane reinforced concrete on things like roads, bridges, dams, hard standings, airfields, water treatment works. If it's grey, made of concrete, we pretty much work with it. And about 24 years ago, 1997, I was introduced to steel fibre reinforced concrete, which simplified a great many things for us in terms of buildability. Having said that, of course, the post-construction defects issues remained extant. In other words, most post-construction defects are probably shrinkage related. There'll be things like joint damage, cracking, curling, delamination, other things of that nature. And it can be quite difficult to explain to a client why their floor slab has developed cracks. About 20 years ago, I began my own consultancy practice, and we specialised in industrial flooring applications predominantly for steel fibre reinforced concrete, but also for mesh fabric and bar reinforced concrete on ground bearing and pile supported applications across most industry sectors in the UK. More recently, I realised, well, this must be about 5 or 6 years ago, that steel fibre reinforced concrete was being applied to multi-storey structures. As an engineer, I wanted to know more. How could this be? A very good friend of mine, Xavier Destre, introduced me to a contact with Primekks in Latvia. In actual fact, he introduced me to the CEO. And I was invited to visit Latvia and meet with them, meet with the team, see what makes them tick. So I went, packed my bags and disappeared, as you do. I only went for a week, but during the course of that week, I was shown a large number of projects, ranging from projects under construction through to completed projects of anything up to about 15 years of age. Elevated slabs, pile supported slabs, ground bearing slabs, etc., etc. And I have to say, at that point, standing on a 15-year-old slab suspended on piles, I had an epiphany. See, it occurs to me that the Primekks system actually eliminated shrinkage. And by eliminating shrinkage, it eliminated all of its associated problems. It's difficult to explain to people until you actually see this in the flesh. When you actually look at an old project, something 10, 15 years of age, etc., and you realise that they look as though they've only recently been cast. There are no big gaps at the perimeters. Joints have remained tightly closed. There are no shrinkage cracks around columns or re-entrance or manhole introductions to the slab or drainage channels or anything of that type. The inserts remain tight. The drainage channels remained undamaged. The joints remained undamaged. I really had to find out more about the system. And that's really where the work began, trying to understand Primekks. And I have to say, it's been very rewarding for me. Well, what is Primekks then? The Primekks system is essentially based on a shrinkage compensated concrete. The concrete doesn't shrink when it's curing, rather it expands slightly. Not a great deal, it's a matter of microstrains. Unrestrained, probably 700 or 800 microstrains or thereabouts. When restrained by steel fibres, however, internally, about 300 or 400 microstrains. It's enough to place the reinforcing fibres into a permanent state of tension and the concrete in a permanent state of compression. Permanent, that's the key word. The steel fibre reinforced concrete, in other words, is now is pre-stressed, or post-tensioned if you will. And in much the same way that a plain reinforced concrete is stronger in terms of flexural strength than a plain concrete, so a chemically post-tensioned steel fibre reinforced concrete is significantly stronger than a traditional reinforced concrete. Now, these are simple statements of facts. The PrīmX system, however, is based and founded on a research and development program. The QA process is laboratory-led. PrīmX, in fact, is the only global concrete solution provider with a fully integrated and fully funded research and development department with its own laboratory facilities. PrīmX actually employs a number of engineers and scientists, some of whom have actually gained their PhDs from research conducted on behalf of PrīmX. So how could an engineer such as myself not be impressed with a unique global company such as PrīmX, led by the numbers? Material science in action. However, it must be said, one of the most interesting aspects of PrīmX is the impact that the technology has on both the built and the natural environment. Let's put this into words. From a built environment perspective, the elimination of drying shrinkage results in the elimination of joints, the elimination of curling, brings a dimensional stability to the entire flooring system. It improves its service life significantly. From an environmental perspective, the post-tensioning of the steel fibre reinforced concrete leads to a reduction of section depth for both ground-bearing and pile-supported slabs. This typically amounts to a carbon footprint reduction of around 40 to 45%. And this is in addition to the potential savings arising from the use of cement replacements, for example. We can confidently state that a PrīmX system can lead to a total carbon footprint reduction of up to 80% when compared to a traditional design. On that basis, and given the environmental pressures that we're under, and let's be honest about it, the rather scarce resources that we're dealing with, why would you not use PrīmX? Let's talk about a case study in the UK. The British Museum Archeological Research Centre at Reading. It's a 16,000 square metre complex comprising 3 linked areas. There's very, very poor ground conditions, brick earth, river deposits, clay. It's got a fluctuating water table level. It's actually on a floodplain, and the development of the site requires a cut and fill. With CBR values of around 2%, clearly it is not suitable, strictly speaking, for a ground-bearing slab, unless ground improvement takes place, which in this instance a structural cut and fill solution was considered and deemed acceptable. The design of the slab required that we accommodate a 100-year design life, horizontal thrust from the portal frames, 100 kilonewton point loads, settlement, early age thermal drying, movement, drying shrinkage stresses, creep, diurnal variation, seasonal temperature changes, etc., and that we designed the slab to TR34 4th edition. The initial design had been provided by others and comprised a 40 Newton concrete at 250 millimeters depth, complete with a layer of A252 mesh fabric. It required the introduction of saw cut induced contraction joints at 6 metre centres, additional steel to accommodate the horizontal thrust, anticipated shrinkage of around about 1 to 2 millimetres per 10 metres of slab would result in construction joints opening up reasonably significantly. It would of course have a porous microstructure, and moisture ingress via capillary action is entirely feasible given the nature of the ground conditions. This in turn meant that a waterproof membrane was required. And of course the solution itself actually exerts a load of around 600 kilos per square metre onto the ground. Significant. We looked at this project and we looked at the design solution, and we thought to ourselves, well, we can improve on this reasonably significantly. And we contracted to produce a floor slab designed as a prime composite slab, so chemically post-tensioned, with waterproof concrete and a section depth of 130 millimeters. Now, I have to say, that is nothing to be scared of. We're dealing with a different type of material to a plain bar reinforced concrete or a typical mesh reinforced concrete. We're dealing with a post-tension material. We could have used tight construction joints. As it happens, the UK installation licensee elected to use a formed construction joint. Okay, we have no problem with that. We eliminated the additional steel requirement for the horizontal thrust, and our anticipated drying shrinkage clearly would be nil. The waterproof concrete was moisture resist to a 3-metre head of water, and therefore the need for a waterproof membrane was eliminated, a significant cost saving to the contractor. More to the point, the dead load on the ground was reduced from 600 kilos to around 300 kilos. In other words, the project not only saved the client money, not only enabled the scarce concrete resource in the area to go a little bit further, in other words, an impact on programme, but it actually resulted in a CO2 saving of around 48%. And that's without consideration for cement replacements. That is simply on a Primekks design. As case studies go, I think it makes a compelling reason for anybody to look at the Primekks prime composite solution for a ground bearing slab, a slab suspended on piles, or indeed an elevated slab. I think that's the bulk of the presentation over from my perspective for the moment. And as stated previously, I have all the time in the world for questions. Please feel free. Let me have your questions. Thank you.